whose venue is and stuff. So differential equations are being used to model some realistic phenomena, like population and stuff like that we discussed in the first lecture. So the equations have the form dx dt equals to some function of x. Now, you will always like to relate this with what you know already from maybe first year. This is not the same as dx dt, a function of t. You see, an example of this here is dx dt is like, say, x minus x squared plus 3 or something like that. X is the dependent variable there, even here. An example of this would be dx dt equals to maybe 2t plus t squared plus 3. See the difference there? This is the stuff you know in first year. This one you can solve easily. If you want x, you can just integrate this 2t plus t squared plus 3 dt. It's easy. This is what you've done in first and second year. I mean the basic courses. So this will be like t squared plus t cubed over 3 plus 3t plus some constant. Can you see the difference between the two things? The top one is a differential equation where x is on the right-hand side. Okay, in your lingo, you always write things as y in terms of x, dy dx. So in first year, you had dy dx equals to x plus 5. When to find y, you integrate it. It can be done easily. To put it in this language here, it's like dy dx is like y squared plus y. Now the y is on the right-hand side. That's a problem. That's not easy. How do you solve that? Some of them are solvable, like we've done already in class. We've done the exponential type, we've done the logistical type. Those are solvable, but in general, they are difficult to solve. And in many cases, they're not solvable. So then, if it's not solvable, I mean, the first prize is to solve it. If you can solve it, then you can tell the model's behavior precisely. You know, at every point, you know for every t value what the x value is. So there's no need to guess at what's going to happen. You can clearly see this model is going to infinity or whatever, blah, blah, blah. But what if you can't solve explicitly for x in terms of t? Then the next best thing is to study the properties of the solution. We can't find the solution, but how about knowing something about the characteristics of the solution? You know, like in high school when you were discussing quadratic equations, you studied the nature of the roots. You could say the roots are rational, the roots are unreal, the roots are real, positive, two roots are real. That's studying the nature of the roots. That's not telling you what the roots are. Thankfully, with the quadratic equation, you can actually find the roots and do both things. But here you can't sometimes solve, but you can study the nature of the solution. That's really the game here. Okay? So I hope that's clarified. Somebody asked me a question yesterday, and I thought that this was a misunderstanding that some people have. Now let's just take an example. By the way, there is a book or a set of notes online. It's uploaded. You have to download it and keep it in your device. So if you want to print it and bind it yourself, you can do that. Many people do that. I don't know why the university prevents us doing that. We used to do that anyway, and students used to like to get a set of bound notes. But for some reason, the university prevented that. So let's take one of the examples that's in the notes. It's given there as exercise. Exercise, as you know, is meant for you. So I don't want you to complain now and go lead a protest outside and toy. Oh, the lecturer is doing our exercise for us, which I'm sure you'll do. In any case, if you want to do that, go ahead. But let me do one or two exercises for you at the beginning. Once you get the hang of it, then you can do it yourself. Right? dx dt, it's got x into 1 minus x squared. So you firstly want to study the fixed points. You want to find the fixed points or the equilibrium points, and then you want to study the stability. Stability means that, oh yes, I didn't say much about stability as a meaning. We just dealt with the requirement for stability, the derivative test. Stability means that if you disturb the system slightly, like if you have a fixed point, and just near the fixed point, you just move next door to the fixed point, the system blows out of proportion, gets chaotic. The correct mathematical word is chaotic. It's a mathematical word. Or if you go to the left of it, it gets chaotic. Then that's an unstable equilibrium point. Okay, in other words, slight deviation causes major chaos. There's actually a branch of mathematics called chaos theory. It's like a honors topic, in case you want to study that. Something else also. Recently I did a paper of my own. What theory was that? Similar idea. Anyway, it'll come back to me. So if you perturb, I should say, if perturbed, the good word there is perturbed. If you perturb a system or disturb it, and it blows away out of proportion, then it's called an unstable equilibrium. It's like, can you imagine a person standing on place a ball here. Take a parabolic hill, place a ball on the top of the hill. Now that equilibrium you could say is unstable because the ball can go anywhere. I mean, it's like you blow next to the hill, the ball might just fall down, left or right. It's unstable. It's there, it looks like it's at equilibrium, it's stationary, but if you just do something, you tickle it or something, it'll fall down. So that's called an unstable equilibrium. It can go nowhere, it has to fall, one way or the other. On the other hand, if you take a same ball, let's put it in a bowl that's in a parabolic shape like that. Now, is it tending to fall down? If it's in a parabolic bowl, isn't it quite stable? It's not going to shift around unnecessarily. Even if you had to slightly tilt the bowl, what will happen? The ball may just jiggle a bit and come back to the beginning, the way it was. So that's called a stable equilibrium. It's a stable equilibrium. So that's the basic differences in the concepts. And we have now learned that the way to test stability is to use there's two ways. Either you can draw the phase plots, dx dt versus x, or you can work out the derivative test, and they give you the same result. Okay? So this is an example here. So now let's do the solution of this problem. So the fixed points are found when f of x is 0. In other words, x into 1 minus x squared is 0. So x is equal to 0 or x equals to plus or minus 1. There are two fixed points. Well, three fixed points. 0, plus, minus 1. Now, let's study the stability. Method 1. Let's do the plot of this dx dt versus x. Okay. So the three equilibria are minus 1, 0, and 1. Now, we need to check. We have four regions. We have one region that's smaller than minus 1, side, one between minus 1 and 0, 0 and 1, and 1 to infinity. There are four regions. We need to see the behavior, the signs in those regions. So what we do is we take a typical number in those regions and work out the sign. That will be typical of the entire region. So if you take something more than 1, 10 or something, take a big number, exaggerate if you like, plug it here. Right, so you're going to get 1 minus 10 squared. Isn't that minus something? Minus 99. Times the x in front. I'm plugging it here, right? 1 minus 10 squared is minus something. Minus something times 10, you can see the answer is negative. So when the answer is negative, You put these arrows like that. Okay. Likewise, now you take the next region between 0 and 1. Take a number there, well, like what? Half. Any number between those two numbers, take half, although it's a bit awkward. Plug it in the yellow thing there. 1 minus half squared. 1 minus 1/4. It's plus 3/4. It's plus. Important thing is plus. Plus times a plus half in front, which is the x, is still plus. So this is plus, so it means you put arrows like this. In this region here, it's going like that. Then you take the region between -1 and 0. What's a typical example there? Minus half. Plug in minus half in the yellow stuff there. 1 minus minus half. Well, minus half squared is still quarter. 1 minus quarter is still just 3/4. It's plus 3/4. But now you got minus half in front. You see now it's negative. This thing points like that. The arrows point that way. And lastly, take the region below -1. Give an example there. -3 or something. Okay, if you take two big numbers, you'll be forced to calculate with them, and then your head will get a bit screwed up. Take reasonable numbers. If you take -3 squared is 9. 1 minus 9 is -8. -8 times a -3 in front. X is -3, by the way. Is plus. So it comes back to plus. So you get this. Okay. Now, when you look at that, you can now make up your mind about stability. That tells you that when the things converge, come together, this is stable. It's stable at -1. At 0, you see some arrows going that way, some arrows going this way. That's unstable. At 1, you see they're coming together. They're attracting. It's an attractor, stable. The same happens at -1. At 0, of course, they are repelling. They are moving in opposite directions. This is not very hard. Eh? If I do the phase portrait, that is a portrait of dx dt versus x. I am really after what is x versus t. We found that there's 3 stability equilibrium points: -1, 0, and 1. And these are the 3. So what we do is we draw those in, and then we just draw some lines here. And we like to see what happens slightly on the top, slightly below this point. And if you start somewhere near this point, where does this thing go? Where does the solution go? Does it go away from the fixed point or not? Or does it approach it? Now, if you look at this region here, more than 1, you can see it's negative. That means if you start from slightly above 1, your curves will have negative slope, like that. That means the thing is going to flow like that. You see it's flowing towards that line. If you start on the left of 1, on this side, you see it's positive. Positive means the slopes are like that. Take the small dashes I'm making. I'm drawing them at an angle of a positive slope. That indicates that this thing is going to go like that. So you can see why at 1 it's stable, because both flows are going towards the fixed point. It's converging on the fixed point. If you disturb it slightly, to the left or to the right, the thing will shake itself back and come back to 1. So it's stable at 1. Okay? Stop me anytime you want, because the thing can be a bit difficult at the beginning. But once you get the hang of it, it's quite easy to implement this. Now let's take 0. So you start off at slightly higher than 0 and slightly lower than 0. Let's start off at slightly higher than 0. On the right of 0, it's positive. So the slope will be like that. So it seems to be that this thing is going up like there, that way. On the left of 0, it's negative. So the tangents are pointing like that, downwards. I mean, it's sloping like that. You see the direction? That's a negative slope. That little piece of dash there is a negative slope. So the thing is going off like that. You can see they are diverging. They're going away from the 0. So slight disturbances from near 0 causes the solutions to move away from the fixed point. That's an unstable equilibrium. Likewise, at -1, we go to -1, you'll find again on the right-hand side of -1, it's a negative slope. If you start off from the top of -1, you'll be following a negative slope. And again, you can see it's going to come down here. If you start off from the just below -1, it's a positive slope. So you start off somewhere there, things are going to go like that, and you can see it's going there. So therefore, this is a stable equilibrium, this is unstable, and this is stable. That's how we classify the equilibrium points, and that's how we make the decisions. Questions? Yes? Oh, no. So just mathematically, if you take x and you increase it by epsilon, x plus epsilon, a small amount, now you want to know whether the graph will actually go completely haywire, which can happen. It can become asymptotic, or it can even bounce around. This can happen. Like you had those limit problems in first year, sine x over x, where things bounce around. Near 0, you get an uncontrollable bouncing. That can happen. So if you have slight disturbances, disturbance means changing x into x plus something, small number. X plus 0.1 or x minus 0.1. That's what we mean by disturbance. Any other questions? Now, let's use method 2, and you decide which one is more efficient. Method 2, this is the derivative test. So what we do is we find, so f of x is x minus x cubed. So we need to find f dash x, which is 1 minus 3x squared. Now we need to plug in each equilibrium point, and according to this test, if you plug in a point and you get a positive, it's an unstable equilibrium. Have a look at the test we gave you in the notes there. It's like a second derivative test for concavity and stuff you learn in first year. So if you take at x equals to -1, f dash -1 will be 1 minus 3 into -1 squared, which is 1 minus 3, which is minus 2. This is stable. If it's negative, it's stable. It's an attractor. At x equal to 0, f dash at 0 will be 1 minus 0, which is 1. And the plus tells us there it is unstable. Plus is bad here. X is 1, f dash at 1 is 1 minus 3 is minus 2. Again, stable. So that confirms what we have already derived. You can see the second derivative test is faithful. It gives you the right results. You may wonder then, why have both tests? Well, remember in the second, the derivative test, what happens when you get a 0 as an answer? There is neither plus nor minus. Then the test is inconclusive. You can't tell. You can't tell from the test. You have to do some other thing. The other thing is often the phase portrait. Okay, let's take shall I take another example or leave this other one? I think this example here Oh, actually, we have to modify this example. Oh, no, okay. It can be done, but maybe it's too hard for you. Exercise, you try out 2a, which is x dot equals to x squared minus 1. You need to classify the equilibrium points there. I think you can do that from your head. And then when you get a bit confident, then you try out the other one, which is x dot equals to x minus x cos x. Well, we won't be able to do them all now together with you, but I say you should just write those down and you try them yourself at home. And if you get stuck then on the tutorial next week, you can bring them forward. The first one is easy, it's just like the example. In fact, you can do it. We can do it fast. You want to do it? Okay. I'll do it in the side. Let's see who wins. Okay, that's it. Derivative is 2x. There are two fixed points, minus 1 and plus 1. You plug in minus 1, you get minus 2. That's unstable, stable rather. And if you plug in plus 1, it's plus 2, which is unstable. End of game. The second problem, unfortunately, is not so trivial. Well, maybe I'll give you a hint there, guys. Huh? You don't want a hint? You see, your fixed points will satisfy that equation. X into 1 minus cos x equal to 0. So then what are your fixed points? And how many are there? X equals 0 is clearly a fixed point. The other option is cos x equals to 1. So then, what does x boil down to? 0 only? 2 pi? Only? 2 pi k. So k times 2 pi. 2 pi k. So the solutions will be x equals to 2 pi k. And for k is an element of some integer. Even 0, but 0 is already there. So that's not a problem. And now you need to discuss the stability. I'm going to leave you at that stage there because there's a million, infinite number of fixed points there. 2k pi, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, 12 pi, and minus 2 pi, minus 4 pi, minus 6 pi. There's lots of them, right? And you discuss it yourself and see what you come up with. So let's leave that at that stage there. I want you to complete that yourself. I want to now move on to some other teaching stuff. Bifurcation of equilibrium points. Bifurcation. Bifurcation means to split up, like a road. If you come to a fork in a road, you can say the road bifurcates. It goes in two ways. So let's start with that. By the way, I'll only go up to about 10 to 11 because I have to attend a meeting. There's a college review process taking place. So after that, you can do what you want. You can carry on with these homework problems if you like. I did tell you tomorrow I'm not here, and Thursday. I mean Friday. You got my mail? I'll always tell you when I'm not going to be here, so you don't have to come for nothing and waste your. Like, remember during the strikes, one of the students wrote, why don't the lecturers tell us if the lectures are cancelled? This is such a waste of money, time, effort, and makeup. So it's quite a, has many ramifications. Oh, by the way, I have children who are at university, so I sometimes see the student, what students are saying from their account. Or they tell us at home, in case you're wondering, hey, who revealed this? The staff members. It's on the Facebook page anyway. Bifurcation of equilibrium points. Yeah, now there's a funny behavior that takes place. Well, let me explain it before telling exactly what it is. Consider a situation like this: dx dt equals to x into 4 minus x squared. Now I'm going to introduce a parameter c. So the bifurcation arises due to some parameter c. This is a parameter. It's something which can change value, or can be assigned different values. But those values stay the same in each problem. So if you take, for example, c equals to 0, then your formula, your equation becomes x dot equals to x into 4 minus x squared. What kind of a graph is that? F of x. Now, if you draw that graph there, it's a cubic function, yes. And so it has roots at 0, minus 2, and plus 2, right? I think it's obvious. Minus 2 plus 2 and 0. And the shape, well, if you get too big, if you take over 2, let's say like 3. 3 into 4 minus 3 squared. 4 minus 3 squared is 4 minus 9. Negative. So it's going to be negative here. So then it follows that the shape, huh? Like this? Right. So the shape will be like that. That's a cubic graph. You don't have to worry about finding the turning points and all that, like you did in high school. All we need to know is the signs. In a way, it's positive, negative, and stuff. That's all. So we don't need to know its exact shape. All right, so now if I take c equals to 1, then x dot will become x into 4 minus x squared. Same graph, plus 1. What is the effect of having plus 1? It shifts 1. It shifts 1 unit up. So then the same graph now, I can just move the entire guy up. And it will look like that. That's when c equals to 1. Likewise, if I take c equals to 2, x dot will be x into 4 minus x squared plus 2. It will shift another 1 unit up. I just want to exaggerate this a bit. There's the undo. Yeah, there you go. You still see there are 2 fixed points, right? In the original one, there were 2 fixed points. The black one, sorry, 3. In the purple one, there were still 3 fixed points. But you see, these 2 fixed points have become closer, and this one has gone further away from 2. It's moved away. Look at the 3 purple dots. Then you look at the green dots, you see the 2 have come very close. Eventually, you can see what's going to happen here. If I carry on increasing C, let's take C equals to 4. X dot equals to x into 4 minus x squared plus 4. You will see that now the thing disappears. One of the fixed points disappears. Right? On the left-hand side, it's not crossing the x-axis anymore. So you can say the 2 left fixed points disappear. So depending on the parameter C, the parameter C dictates whether there will be fixed points, how many there are, and depending on its value, it can be, in this example, 3 fixed points, it can be 2 fixed points. When will there be 2 fixed points? My pictures just show you the situation with 3 and 1. When will there be 2 fixed points? How must the curve move, or how much? Even if you don't know how much, what do you understand by it? What must happen? Okay. Yeah, it must move just enough so that the green one, for example, will scrape the x-axis. You know, there's some number, some magic number that you just move it slightly up, it'll just touch it. Tangents, it'll be tangent. You just scrape the x-axis. So that point of tangency where the blue one is almost there, and the other guy on this side will make 2. And then if you go slightly higher, like the blue one, now there's there's only 1 fixed point. So you can have 1, 2, or 3 fixed points in this problem. Can you have no fixed points? Can you have 0 fixed points ever in this problem for any value of C? No. At some stage, that right guy is always coming down. He must hit the x-axis somewhere. Doesn't matter how high you lift him up, that right arm is always going to come down to meet the x-axis. Can you have more than 3 fixed points? Not in this problem. If you have x to the power of 4 in the question, yes, then it's possible. But now, this problem, you can only have 3 options, either 1, 2, or 3 fixed points. All right, so if I can just draw these plots here, how do I express it for you? I used up the space. Anyway, let's just say C equals to naught. Let me redo it here. Now, if you look at the number line, we had minus 2, 0, and 2. At first, we had 3 fixed points, minus 2, 0, and 2. On the right-hand side of 2, it's negative. Then it's positive there. And it's negative there. Positive there. So from a stability point of view, this guy is stable. This guy here is unstable. This is like the first example we did. X into 1 minus x squared. Same thing. This is stable. But you know how to tell? The arrows. If the arrows come towards each other, that's a stable point. If the arrows go away from each other, it's an unstable fixed point. All right, now if you take C equals to 2, I won't take them all. Let's just take C equals to 2. For C equals to 2, I think I drew the green one. So you have minus 2, 0, and 2. But those are no longer the fixed points. The fixed points are now between, these are the 2 fixed points. And 1 on this side here. You see these two have become close to each other here on top. And 1 on the side here. In the top left. So 1 just passed 2, and these 2 have become close. And the things are almost the same. You see, that's going to be, the shape doesn't change. You're going to have a similar thing like this. Right? On this side, you'll have less than. We have more than all the way. So the same kind of, the stability doesn't change either. The stability stays the same. You'll have different fixed points though. Fixed points have changed. And if you overdo it, you go up to c equals to 4. Then you lose a fixed point. There's only one fixed point, and it's near 2, you have it here. On this side, it's still positive, and on the other side, sorry, negative. Other side is always positive. Because on the left-hand side, the graph is entirely on the top. It's positive. So then this is now the only fixed point. It is, sorry, not that one there, not that one. Here, 2 comma something, or 3 comma something, whatever. So this is stable. Let me quickly cut to a Mathematica file. By the way, you guys can Mathematica free of license. Mathematica is a very expensive software program, and all students are entitled to download the university machines and on the home machines. You have a site license. So you should learn how to use it. It's a very powerful tool. It's the most powerful mathematical computing tool in the world. There is Maple also, which is the other one we use, but Mathematica has more muscle. Maple has better graphics and stuff. And then the one that engineers use, MATLAB, that's more about graphics. But the real gumption, the real muscle is in Mathematica. Stephen Wolfram was a mathematician, and he developed this package, which is now big. It can do so many things. I'm just going to use it now to plot. You've got to learn the syntax. Plot, use capital P-L-O-T. Open square brackets. What is that function? X into 4 minus x squared. X times 4 minus x squared plus c. And then I got to give the domain. Say x is from minus 6 to 6. But now it won't draw anything because I didn't say what c is. So let me say c equals to 0. We went on the wrong layer. Okay. You see the plot range is from 0 to 200. Let me make the plot range something more manageable. Plot range. Let's make the plot range from minus 10 to plus 10. Okay, that's what you like to see now. So when c is 0, c is 0, or c is 0, you get that. I just want to delete that line of code. Now, let me change c to 1. Keep an eye on the fixed points. You see there's 1, 2, 3. We know those 3, right? Let me change it to 1. Shift enter. You see it's no longer exactly minus 2. It's no longer 0. It's moved in. Because the graph has gone up 1 unit, as you predicted yourself. If I take c equals to 2, it gets even higher. The 2 fixed points come closer. Other one goes outside of 2. Take c equals to 3, which I didn't draw earlier. Almost scrapes the graph. The magic number is 3,07, I think. It's easy to find. You differentiate and make it equal to 0. Find the derivative and stuff. You've done it in high school. But now if you go to c equals to 4, now it escapes. The left-hand fixed points are no more there. It's gone up. There's only one fixed point. Okay? So you see, you can carry on like this. If the parameter c is more than the tangential value, like 10 or whatever, then, well, I fixed the range to my plus 10, but you see it's on the top. There's still 1 there on the side. On this side, still 1 there. On the top, the graph has become too tall. I should allow more plot range. Okay, so that brings me to the definition then But what do we mean by bifurcation point? Bifurcation point is a parameter that causes the fixed points to disappear. So the definition. Well, there's two aspects. Bifurcation point where for some parameter values like c equals to something, the fixed point disappears. Disappears or reappears or appears. Some parameter values cause fixed point to go away and come back. And it could also mean a point where the stability changes. The stability changes. So maybe for some parameter values the thing is stable there, for other parameter values is unstable there. So then that's what we call a bifurcation point. Right now, let's take the first type of bifurcation point, which is well, we have done already. The first example there was an example of a bifurcation with the parameter c varying there. We found that some fixed points were lost. Now let's take, let me label it as the book does, 1.5.1, saddle node bifurcation. Saddle node bifurcation. And the generic example, or the generic form, or what we call a normal form, is x dot equals to r plus x squared, or x dot equals to r minus x squared. That generates a saddle node point bifurcation. You'll see the stability changes. Okay, r is a parameter. So let me do half. I'll consider r plus x squared. You discuss r minus x squared yourself in your own time. Consider x dot equals to r plus x squared. So r is a parameter. So r can take on a number of different values, like 1, 2, 3, 4, and it will have the effect of moving the graph up and down or whatever. So what are the equilibrium points? Equilibrium of fixed points. That's when r plus x squared is equal to 0. This means that x equals to, x squared is equal to minus r. This means that x equals to plus minus square root of minus r. And from that, you can say it only exists, the fixed points only exist if r is negative. In this example, because you can't find the square root of a negative number. So when we say root of minus r, if r is negative, then it will become positive, minus of a negative. But if r is positive, then you're dealing with the square root of minus 3 and stuff like that, which is unreal. It's a complex number. There's a whole game to be played with that, but we're not going to go there. Next year, if you survive to Math 356, which I would normally take myself, I will show you how that works there. Complex analysis and Fourier's theorem. So we are only going to discuss r, well, we will say that the fixed points exist only for r less than 0. So let's just discuss that. Now, let's just say, what is f dash x? Differentiate the right-hand side, you get derivative of r is 0. Derivative of x squared is 2x. So I'm differentiating, I'm differentiating this green guy here. Derivative of r is nothing. Derivative of x squared is 2x. Let's plonk in the two fixed points. F dash at root minus r is 2 root minus r. What can you say about that? If r is negative, this will be positive, right? This will be an unstable. Note r is less than 0. On the other hand, if you take f dash at minus root minus r, which is the other fixed point, you get minus 2 root minus r, which is positive. No, I mean it's negative. So stable. Remember, root minus r is only works for r being negative, and in those circumstances, you get some positive answer, root of minus of minus. Then you multiply by minus 2, it'll become negative. If at any time you're confused, then just stop me and we can then discuss it again. So just a few diagrams. Let me do the diagrams for x dot versus x. So we have two fixed points. One is minus root of minus r, other is root of minus r. Okay, that's a straightforward parabola. It's a straightforward parabola. So if we are considering the case r less than 0. So then it's a straightforward parabola. It will have a shape like this. So here it's positive, here it's negative. So this side is positive, like that. This side is negative, this side is positive. So from that, you can see that this here is stable, and this guy here is not, unstable. How do we know that? You can see in one case the arrows are coming together, that's stable. Other case the arrows are going away, unstable. And that's the prediction we have made here. That's what we said. We have dealt with that matter. Okay, let's take r equal to 0. We have to cover all our bases here. If you take r equal to 0, suppose the parameter r has the value 0, then it's like x dot equals to x squared. The parabola y equals x squared. It's a straightforward parabola like this. Sorry, the diagram is a bit wonky here. It's a parabola like that at 0. So it's positive actually on both sides. So the arrows go like that and like that. Because the parabola is positive on both sides. The gradient is positive, in other words. So then this is an unstable equilibrium. Note here, f dash at naught would have been equal to naught. So this would have been inconclusive. If I attempted to discuss the case r equals to naught with this derivative test, I would not get a result. But if I reduce it to a study of the phase portrait, I do get the conclusion that it's unstable. Because the arrows are heading, on the left-hand side, they're heading towards 0. On the right-hand side, they're heading away from 0. So they're not coinciding. They're not coming together. And the third case to consider, although I've said that we are considering r r less than 0. That's the only one that matters. Of course, r equal to 0 as well. But we must just finalize the case r more than 0. If you take r more than 0, like 1 or something, 1 plus x squared, isn't it true that the parabola will be something like that? It'll be above. So there are no fixed points. Under those circumstances, there are no fixed points. Right? Any questions there? That covers that. So what I want you to do as part of your homework, something you can think about maybe for tomorrow's period that I'm not here, I'm sure you'll come to class and carry on working on, even though the lecturer is not present. Nah, I'm just kidding. You discuss x dot equals to r minus x squared. I've done the slightly harder case. Your one is a little easier. This one will work only for r positive, but it won't be exactly the same as that. There'll be some change. Yes. Oh, yeah, one more thing before I leave that problem. Let me squeeze it in here. I'll just move this statement to the bottom. I move it. Okay, leave it there, it's no problem. But let me talk about a bifurcation diagram. You see, we need to see this thing here before we draw it. So, bifurcation diagram. Bifurcation diagram. So, this is like the x versus r. So far, we've got x dot versus x. But how does x behave with t? X versus t, rather. Or r, if you want, because r is a parameter. It's changing with r. So, let's take x dot equals to r plus x squared. So we found that the roots were plus minus square root of minus r. So the bifurcation diagram looks like this. This time it's x versus r. X versus the parameter, how things change with the change in the parameter. Now you'll find that when r was less than 0, this thing was alive. So it had the shape of root of r like this. This is minus root minus r. And when it was positive, not positive, sorry. For the other case, plus root of the plus branch, it's like a sleeping parabola, right? This is the other branch, plus root of minus r. There's two branches, minus root of minus r, plus root of minus r. Now you may wonder, why did he put one in dotted lines and one in solid line? Well, what do you think is the reason? R less than 0 only applies. You can see at minus root minus r, this is a stable branch, and this is the unstable. So the unstable branch will always be in dotted lines. And you can see this point 0 here is where the stability changed. That's a bifurcation point. This here is the bifurcation point. That's where the stability changed. So in other words, I'm graphing x in terms of r. How does x change with r? the function is x equals a root r, or root minus r, plus of it and minus of it. Now when you do your part, this one here, that's that. You should find that the game is here. And the top part there will be irrelevant. It will be stable, the bottom part will be unstable. So you follow exactly the same process and see if you can generate that bifurcation picture. Became a bit cluttered there, lots of stuff there. Okay, there's two more types of bifurcations before we finish up. All right, so we said that you either have so this is called a saddle node point. Let me make that point. Write that next to it, saddle node point. Saddle node point. Because now I'm going on to another type of bifurcation called a transcritical bifurcation. There's some hectic words here. Transcritical bifurcation. What does it mean? It means here we'll have a change in stability of the fixed point. Change. The previous one was about how the fixed point appeared and disappeared. So that was called a saddle point. Now we have where the stability, when 1 minute the thing is stable, when you change it, consider a different parameter value, it can become unstable. The same point. That's what's going to happen. Did I draw the picture? Okay, well, okay, let's take the classic example, generic example. Generic means it's the typical example. Generic form. X dot equals Rx minus X squared. X dot equals to Rx minus X squared. There's now an X next to R. That changes the game altogether. So let's do the usual fixed points. Will be Rx minus X squared equal to 0. This means that X into R minus X equal to 0. X equal to 0 or X equals to R. Stability. Find the derivative of that, f dash of x. Remember the right hand side is f of x. Differentiate the right hand side, I will get r minus 2x. Firstly, plug in 0 because that's a one fixed point. F dash at 0 will be r minus 0, which is r. Now you see that if r positive, then it's unstable. Straight away you can see that there's a problem happening here at 0. If r negative, it will be stable. So it depends on r. So there you see the same point, 0, can have two characters depending on r. That's what we call a bifurcation point also, where the stability changes depending on a parameter. The parameter in this example being r. Now the other guy to consider is f dash of r itself. So this will be r minus 2r. R minus 2r is minus r. Once again, you've got two possibilities, two faces. So if you have r positive, now what happens? What happens if r is positive here? Stable or unstable? If r is positive, minus r is negative. Negative means stable. So it will be stable. So, stable. And of course, if R is negative, it will be unstable. So you see there's a change in the stability at the requisite point. If I may use graphs, let's use a graph of x dot versus t. Let's consider firstly the case R positive. R positive. So then your graphs look like this. Like take R equals to 1, x minus x squared. So you'll have 2 points will be 0 and 1. So 0 and R. And it's x minus x squared. It's a parabola that's upside down, isn't it? Think about it. The shape would be this way. X minus x squared. Minus x squared is upside down. So when R is more than 0, and then if you draw those arrow stories that I showed you earlier on, this is like approaching. This one here is positive. This side here is negative. You can see this guy here is stable, and this guy here is unstable. If you take R less than 0, game is slightly different now. Now you take like minus x squared. It's still going to be minus x squared that dominates. It's still going to be an upside down story. Just to, for example, minus x squared. You can take your own example. So it'll become like minus x into 1 plus x. So the roots will be like 0 and minus 1 now. Right? And now the game is here. It's the same kind of shape, but there is a change. You can see so the 0 is there and the minus 1 is there. This side it's negative. Here it's positive. Here it's negative. So where is the stable point now? Minus 1. It's stable here. Huh? No, it's unstable. And at 0, because of the arrows, now the 0 is stable. So in the blue picture, the colors are all wonky on the top. It's blue here. The top one has got 0 being unstable. The bottom one has got 0 being stable. You see, there's a change in stability brought about by the value of R. This is called a bifurcation point. So for R more than 0, R more than 0, x of t equal to 0 is stable. For R less than 0, x of t equals to 0 is unstable. No, other way around. Unstable, and here it's stable. Am I right? It's from the picture above. Unstable there, that picture, and stable here. Okay, so that's the case of a transcritical bifurcation at R equal to 0. So we can say there's a transcritical bifurcation at x of t 0. Any questions thus far, guys? I hope you're carrying, you're keeping yourself awake and alert. And I hope you're following the arguments and the discussion. It's basically definitions and practicing what the words mean. Tutorials are similar. It will test your application of what you're learning. You need to engage with them yourself. You can try working them out at home also, before Wednesday next week. Don't wait for the tutorial. We now go on to, we end off in fact. One more big word. I thought you had enough of big words. Supercritical. Supercritical pitchfork. Pitchfork bifurcation. Supercritical pitchfork. Pitchfork, you know what a pitchfork is? What shape does a pitchfork have? Ah, it's a pitchfork. It's a kind of garden stuff that you use, but with 3 prongs. This one here at the end, that's the kind that you'll find that happen here in the problem. Okay, so let's see how this happens. So the normal form, I must gallop a bit because of the time. The normal form is x dot equals to rx minus x cubed. The pitchfork one it has some symmetry, but I'll show you as we go along. I mean, this doesn't mean much by me saying it here. The example used by the author of the notes, which is Professor Banda from Maritzburg, is that it's like a pole, and you've got a force acting on a pole. That pole can split up into 2 ways, like a pitchfork, and break up. Maybe that's a good example. I don't know. I actually don't know this area very well. This is not my area. But the mathematical side is pretty straightforward. So let's take the fixed points. You have to solve f of x equal to 0. So this means that rx minus x cubed is 0. That means x into r minus x squared equal to 0. X is 0 or x equals to plus minus root r. And of course, only r more than 0 counts. R more than equal to 0. So let's test the stability. F dash of x will be r minus 3x squared, differentiating with respect to x. Plug in each of the equilibrium points, f dash at naught, the r minus naught, which is r. R is positive here, so this is going to be unstable. For r positive, it's unstable. Do I discuss? Okay, I will discuss r negative. F dash of root r will be r minus 3 times r, because x squared is r, it will be minus 2r. So this is going to be stable if r is positive. Likewise, f dash at minus root r is r minus, again, 3r minus 2r. Stable if r is positive. Uh, what do we do? Okay, let's do the plots. Let's take some graphs. X dot versus x. We consider all three cases. I just remember the function is x dot equals to rx minus x squared x cubed. So the roots are minus 0, minus root r, and plus root r. But now, if you take r less than 0, if r is negative, what we said you don't get roots. But let's see what the shape of f of x is. Look at this thing here. R is less than 0. Let's take minus 1, minus x cubed. What kind of shape will that generate? It's not a cubic function, by the way, guys, so it's going to have like a positive and negative side. It's going to cut the x-axis somewhere. If r is 0, it'll cross at 0. But if r is some negative number, say minus 1, what kind of a shape do you think it'll have? Let's convince you with Mathematica. So let's put this as r. I said r is minus 1. And the function is, what's the function? Rx minus x squared, x cubed, yeah. R times x minus x cubed. We don't need this thing here. Okay, that's good enough. There you go. What shape is that? It's a cubic graph. So when r is negative, you get that kind of a shape. Let's put a minus 2 there, just to see that things don't go off beat. It's the same shape. Let's put a minus 3 there. It's the same shape. Okay? Put a 0 there. Same shape roughly. Still positive and negative. Now, what happens if you go on the positive side? Let's put r equals to 1. Ah, game changes. Now there's 3 fixed points. If r is positive, let's say 2. Again, 3 fixed points. And so on and so on. So that gives us a character of the root coming back here. So if r is negative, you're going to get a situation like this. Like that. So here is negative. Here is positive. So it's stable at r equal to 0. Stable there. There is a fixed point at 0 and it's stable. There'll be a fixed point because x into r minus but whatever equal to 0. X equal to 0 is always a fixed point here. Okay, now let's take now the second graph. If things are not adding up in your head, please let me know. Minus root r, 0, and root r. This time we'll take r equal to 0. Again, we found that the shape was the same. Okay. This branch here is negative, so we can put arrows like that. This branch is positive, put arrows like that, all over. So again, it's stable. Stable at 0. 0 is a fixed point no matter what happens. And then finally, this is x dot versus x. X dot versus x. Finally, no. Finally here, the really important one, when r is positive, minus root r plus root r, 0. This time we had, it was like x minus x cubed. So when x is big, so like 3 minus 3 cubed, it will be negative. Like this? Was it like this? Yeah, so when x is, say, big, x is like 3, so it's like 3 minus 3 cubed is negative something. You can just check this out. Here's the shape here. That's a generic shape. So then, oh. So this side is negative, here it's positive, here it's negative, here it's positive. Now tell me which are the stable points. This one here, what can you say about that? Stable. This guy at 0, unstable. Things are moving opposite direction. And this guy here at root r, stable. So that's the situation if you have different values of r. 10:53. I have to go to the meeting. Let me stop here. I'm going to just a picture to draw here, which is the pitchfork. Let me finish the pitchfork. How can you stop with a cliffhanger? So now we do the phase portrait. It's going to be x versus r. Okay. So this is r. When r is negative, you have this thing here on that side, the pitchfork. When r is positive, on the right of 0, it was unstable. And then you had the two branches, root r and minus, both were, you had this x equals to root r, this is root r, and x equals to minus root r. So, minus root r. Okay. So where am I getting all this from? You can see the stable point here. Oh, this one here is this guy here, and this guy here is the bottom branch here. At 0, you have an instability. On the right-hand side, it's unstable, and on the left-hand side, it is stable. Therefore, can you see why we call this a pitchfork now? This is pitchfork. Okay, there's one more case to be done in the next example. Maybe we'll spend a little more time on that so you can get a better grasp of this. But I have to stop at this time and get to this meeting at 11. Very good.